Hello everyone, today I'll present my paper on uncertainty-aware vision transformers for medical image analysis. Large-scale pre-training with vision transformers offer a competitive alternative to CNNs, especially because practitioner can pre-train the scalable vision transformers with very large-scale image dataset such as ImageNet 21K. However, efficient uncertainty estimation in transformers is a challenge and is still rather unexplored. Deep ensembles and Bayesian neural networks, some of the classic methods, require rigorous training and is infeasible due to the high number of ViT models parameters as such, not really practical in applications such as real-life medical imaging. And a proposed solution is to directly inject stochasticity into the vision transformers. And so these are our following contributions. The first one is we embed stochastic Gaussian embeddings in all layers through Gaussian parameterization of the weights. So in a deterministic case, we normally embed like the vectors in point vectors with only one single weight, but in a stochastic one now we embed all the weights and we embed all vectors into both mean and variance. So we have mean and variance weights, and they are following the normal distributions. And because we are passing uncertainty through all the layers of the transformers, we need to modify the attention as well. So in a deterministic attention is a dot product between the query, key, and value vectors, as we see here. And in the stochastic one, now we have distributions of the query and key and value vectors. And one way is we couldn't really do a dot product from there, so we could find the products between the distributions or the Gaussian distributions. We try to use a FID distance, which is a negative 2, it's like a formulation of 2 Wasserstein distance of the distributions. So from there we can calculate the difference or the product or between distributions with the FID distance here. And this facilitates stochastic attention, so leveraging uncertainty awareness in the training. And lastly, we have the distributional regularization with the FID distance. So in a classical classification task, we only have a cross entropy loss, and now we add 2 additional regularization terms. With here, Z out is the output vectors, the output embeddings, and then Y plus is a positive and Y minus is the negative examples. So I'll explain a bit more about positive negative examples in the next slide. But these both work as contrastive regularization terms that foster uncertainty and distance awareness in the training. And each terms, they work by embedding similar representations closer together, while also pushing dissimilar representations further away from each other. And so this is the flowchart of the contributions. As we see here, we have the input of an ISIC 2019 skin lesion image, for example, and then per usual in a vision transformer, you split it and tokenize it, but in the tokens we split it into 2 again. We split the same tokens, actually we just copy it into 2 copies, and in the 1 copy perform augmentations and also masking as usual and then we feed this one as a normal input, the Z embedding, and then this will be fed into the Gaussian embeddings, and this will be passed as distribution throughout the network. And then we have the positive examples, which are the same tokens, but these are not augmented, so this is considered positive examples. And then we also embed this into distributions by feeding it into the frozen train encoder. And then we also sample a negative example, which is image from another class, and then we also tokenize it and embed it into distributions. And then the distribution of the output embeddings and on the distribution of positive and negative examples, they are fed together and fed into this loss function, which try to push the embedding closer to the positive example and further from the negative example. So the experimental setting, all experiments are done with the default ViTB architectures, and the dataset is the ISIC 2019 skin lesion dataset, and with the classification task, all models are previously pre-trained with ImageNet 1K. And for experiments, we have in-distribution calibration predictive performance, near OD evaluation, and few shot learning. And these are the evaluation metrics. These three first ones are for the calibration performance and also selective accuracy. Also consider the predictive performance and OD ROC for the OD evaluation. And here we have the quantitative results, and we have also ER and NFSEB. These are also two methods which are shown to work for uncertainty calibration in ISIC datasets. And as we can see here, our method outperforms also like the classic baselines, ensemble MC dropout for all these tasks, and also performing very close to the ensemble one for like the ensemble baseline for few shot learning. Here you can also see that our method embed uncertainty better than deep ensembles, for example, in a qualitative way by embedding far away points as uncertain as blue and nearby points as yellow.